All righty, let us get started. So today we will be doing our exam 2 review. The exam 2 will be on Monday. And it'll be done just like the previous exam. Monday morning, the test will be posted on the Canvas. You download, it'll be a PDF in the module section under exams. Download it, work out the problems. All the problems are calculation type, just like before. So you work out the problem, show all of your work, obviously. That allows me to give you partial credit when necessary or when available. And lets me make sure that, you know, you're doing your work. You're not just copying the answer from someone or whatever. And then box your answers. That's for my benefit, just so that I can, you know, it's more organized looking. I know what is your solution versus what's just part of your work. In terms of the answers, as you know, we haven't been really following the rules of significant figures or anything like that in this class. That's just my own choice. I felt, especially because this is not a class where I'm trying to train people who want to be physicists, I'd rather concentrate more on, you know, the physics itself, understanding how to work the problems, rather than all of the details and formality of the appropriate format of an answer or things like that. That's not as important to me. Obviously, if you're going to go on to do some kind of scientific work, whether it's in biology or some other field, and you're doing official work, then those types of things are important. Things like significant figures, reporting your results is important, and you need to know those rules. But for this class, it's more about the physics of it rather than those other details. So my suggestion when given an answer, usually just give 2 or 3 decimal places, and that's sufficient. Usually if you give 2 or 3 decimal places, then whatever rounding is done in the answers and things like that comes out okay. There's not a lot of difference between what I would get as an answer and what you would get, as long as we're doing it correctly, of course. So I would say that when given an answer, 2 decimal places is usually sufficient. Also, definitely you need a calculator. You are working out the problems. You're not just showing the equation. You're not just showing the numbers in the equation. You actually have to get the answer. So make sure you have access to a calculator at the time. And so anyway, you work them out, box your answers, and then when it's completed, you go back and submit it back onto Canvas, just like the previous test. The deadline, of course, will be due 11:59 p.m. that night. So you have the full day. This is not held just at our class time. It's not just 1 to 1:50. You have the full day to work on it. That way, if you know you're on campus for certain classes, you can wait till you get home and you're in a more peaceful setting, and you can just work on your test there if you want. Even though it's due by 11:59 p.m., that doesn't mean you have to wait till then to submit it. In fact, I suggest that you submit it as early as you can. And the reason is because it tends to pop up that some technological problems happen, and either it's not submitting it, your internet goes out because Cox Cable is not doing well, or something happens. And it's a lot more easy for me to recognize that it's a legitimate complication when you tell me before the deadline's over, hey, look, I tried submitting it, but it's not going through. I just want to let you know I have it done. Here's a copy of it. Rather than tomorrow morning, I get an email saying, hey, I tried to submit my test yesterday, but it wouldn't go through. Here it is today. Well, you may be being completely honest, Or you may be lying and it's just you didn't finish it yesterday, or you forgot, or you needed more time, or whatever the case. I have no way of knowing which is which. So try to submit it early. That way, if there is a problem, you can email me, let me know ahead of time, and then I can let you know how we can handle the situation. But you have till midnight, 11:59 p.m. to submit it back onto Canvas. Oh yeah, as was true of the first exam, the same is true here. Although this is being held as an online test, that does not mean that I'm changing the format of the test or I'm making it longer or more complicated since you are at home to take it. I'm going to create the test as if it's an in-class test that you'd be taking, which means the test will be made for a 50-minute test. And what I found is, generally speaking, on the average, 6 to 7 questions seems to be a good number when working full computational questions out to be done in 50 minutes. Most people can finish the test in 50 minutes at this length, and so that's what you can expect. Now, depending on the topics, some of the topics may be very quick to solve, some are a little bit longer, so maybe there may be a question or two more or less, but somewhere around 6 to 7 questions is what you can expect here. Let's see. Any questions about the formality of the test before I move into the actual topics, what you can expect on it? Yeah, basically everybody now, whether you've had me in a previous semester or not, you've all had at least the first test with me. And so you know what the test looked like, you know how it works. So there's not going to be anything surprising here. It's going to be the same kind of format as your first test, just on this new topic. Now, the way I do exams in this class, the final exam is cumulative, but all the mid-semester exams, they are only on their own specific topic. So this particular test is only going to be on those topics that were covered after the first exam, which means it's on fluids. So fluids is the topic. Now, under fluids, of course, we found that there were several subtopics we went over. The first that we discussed was Bernoulli. So we had Bernoulli's principle. And what Bernoulli's principle was, first of all, the equation, P1 plus 1/2 rho V1 squared plus rho GH1. That is the total net pressure, or change in pressure, but the total net pressure on a system at some location is constant, which means if you look at this location, the beginning of the system, and you add up all the things about pressure there, then you look at some other location in the system and you add all of those pressure things up, you get the same number. So this is equal to P2 plus 1/2 rho V2 squared plus rho GH2. That's what this means. The total net pressure initially is the total net pressure finally, but that pressure can be broken up into several pieces. Some of it may be due to like a pump system. Some might be due to the speed of the fluid running through the pipe. Some has to do with how the pipe changes height. You go up to the second floor or the basement. So the total pressure is broken up into several pieces. And if you add up all those pieces, the total pressure doesn't change. What can change is maybe the fact that the size of the pipe changed from one location to another. Well, what that does is it changes the velocity. So the velocity may go up in going to the second location, but if the velocity went up, then something else had to change to make it so the net pressure stays the same. And so what you find is the pressure goes down when the velocity goes up. And so obviously this is very, very reminiscent of conservation of energy, which is kinetic initial plus potential initial is kinetic final plus potential final. Same kind of a thing. You have a system, the total energy is made up of several pieces, the kinetic energy, gravitational potential energy, spring potential energy, and so forth. And if you add up all of those terms, you get the total energy. If you look at this part of the system, the total energy is some number. You look at another part, it's the same number. However, how the energy is split up into the different pieces can change. That's what Bernoulli does, but instead of energy, we're talking about pressure. Now, along with Bernoulli, we found that we need a secondary equation which helps us derive some of this information. For instance, when you have a pipe system and I say the pipe constricts to some new size, well, there's nothing in Bernoulli that tells you about the size of the pipe. I mean, there's no R, there's no distance here, there's height that tells you how the pipe moves up and down, but it doesn't tell you about how the size of the pipe changes. So we need a second equation which can relate the size of the pipe to something that's important for Bernoulli. And what that was a continuity equation. So the continuity equation, what that says is that the size of the pipe relates to the speed of the fluid running through the pipe. And what it says specifically is the area, the cross-sectional area, that is the size of the opening of the pipe in one location, times the velocity of the fluid running through that part of the pipe. This thing is called the volume flow rate. It is how much water is flowing through the pipe per second at this location. So it might be something like a gallon of water is flowing through the pipe per second here. And continuity says that flow rate is constant. So if you change the size of the pipe, the velocity will also change to keep the flow rate constant. And so it says the size of the pipe in the second location times the velocity of the fluid in that second location must be the same number. So you have a certain amount of water coming in, the pipe changes, the velocity will change such that you get the same amount of water coming out. And we remember that the easy physical example is placing your thumb on the end of a hose, makes the water shoot out further because the water speeds up. Why does it speed up? Because when you put your thumb on the end of the hose, you've constricted the pipe, you made the pipe smaller. And so to get the same amount of water coming out of the hose per second, given that there's now a smaller hole, the water had to speed up so more water can shoot out faster. And of course, to go along with this, the area we're talking about, all the questions we're going to discuss are pipes that are round pipes, cylindrical pipes. We're not going to talk about square pipes or anything like that. And so the area is just pi r squared for that size of the pipe. Okay, we need the radius. The radius tells us the size of the pipe. So with these two equations, we're able to solve this style of question. You have a pipe system, water's flowing through at a certain speed, the pipe is a certain size, then the pipe changes, goes up to the second floor shower, the pipe constricts to this new size, and I want to know what's the change in pressure. Well, the way you would solve it is you want to use Bernoulli. That'll give you the change in pressure. P2 minus P1 means the change in pressure. But in order to solve it, we need all the other terms. The problem is, with this particular example, we don't know how fast the water will be moving in the second part of the pipe when it's up at the shower. So then we use continuity and say, okay, what will V2 be if the size of the pipe changes to this new size? So you use continuity, you calculate V2, you can now plug that number back into Bernoulli's equation. From there, you'll have all the numbers. You can now solve for your change in pressure. So Bernoulli and continuity always go together, or generally speaking, they go together. So that was the first kind of major topic or subtopic of fluids, Bernoulli's stuff. From there, we also had a different subtopic, which was kind of the pressure-depth relationship. And this relationship talked about the fact that as you go under or deeper and deeper into a fluid, that fluid applies more and more pressure to you. And so to calculate how much pressure you would feel given you go underwater a certain depth, you use the equation pressure at this depth is rho, the density of the fluid you're in. Are you in water? Are you in honey? Are you in air? What are you in? That's the density of the fluid times G, 9.8, because we're on Earth, times H, which is how deep you go. Okay, so in this case, H doesn't mean height per se. It means you went 50 meters down, so H is 50. And so this is a nice relationship, a nice equation. A diver dives down 100 meters under the surface of the ocean. How much pressure will he feel? This is what you would use to calculate that. Now, along with this was this concept of what's called gauge pressure. So when we discuss pressure, there's two things we may find important. The first is how much pressure, what's the total pressure felt by something? Now you could call that total pressure or you could call it absolute pressure. It means the same thing. However, what may also be important, or what may be more important than the total pressure felt by something, is how much the pressure changes from where it was before to where it is now. And that type of thing would be called gauge pressure, or it's related to gauge pressure. So what gauge pressure is the total pressure or the absolute pressure that something would feel minus how much of that pressure is just due to the atmosphere by itself. Because living here on Earth, every single object is in the atmosphere. The atmosphere is made of air, air is a gas, and a gas is a fluid. So everything is in some fluid. We call it the air. And we know that if you're in a fluid, the fluid applies a pressure. So just sitting here on Earth, wherever you are, the atmosphere is applying a pressure to you, and that pressure is a certain number. 1 times 10 to the 5th, something like that. So there's already a pressure everything on the Earth feels. However, because everything feels this pressure, then it's not really that important. Everything feels it. It's like if everybody in the United States was given $1,000, so everybody has 1,000, and then you get paid on top of that. Well, that original 1,000 is kind of immaterial, because if everybody got it, or let's say a better example is you're in a class, and I give everybody 10 bonus points. Everybody in the class gets 10 bonus points. Well, that doesn't really change anything. All it does is everybody's number goes up by 10, but the relative average of everybody, it doesn't make one person go ahead of another person. If you were in 4th place, you're still in 4th place after everybody got the bonus points. So who cares? That bonus point doesn't matter. Here, the atmospheric pressure, for the most part, for most things we do, we could just ignore it because we know everything's there. So what is usually more important than that is how much extra pressure is there. And I use the example of like an empty bicycle tire. You go to pump up a bicycle tire. When it's flat, you plug the pump in. The gauge on the pump says it's at 0 pressure. That means it's flat, it's empty. But of course, it's not really empty. It's got the atmosphere in it. So it has some set pressure, but who cares that there's atmospheric pressure? Because that's our 0 point. That's our starting point. Everything feels it, and then there could be more pressure than that. And so what the gauge pressure tells you is how much more pressure an object feels because of whatever it is you're doing. A diver going underwater, I don't care that he feels the atmospheric pressure, because everybody does. Of course he does. What's more critical is how much more pressure will this diver feel since they're under the water. And so that's gauge pressure. So these two things kind of go together in the sense of when I give you a question, like the diver diving underneath the water, and I ask, what pressure will this diver feel? Well, you have to be very careful to read and not kind of rush through the question and understand, am I asking you for the gauge pressure or am I asking you for the absolute pressure? And the rule I use for this class, and this is not some standard rule where this is true universally, this is just for our class. The rule I've made up is you always assume I'm asking for the gauge pressure unless the question specifically says, tell me the total pressure or tell me the absolute pressure. Okay, if I ask for the absolute pressure, then of course you give me the absolute. If I don't say anything like that, just say what pressure will the diver feel, then I'm assuming, or you're to assume, I want the gauge pressure. And so this pressure depth relationship equation sitting there, that's a pressure, that's a gauge pressure. Because nowhere in that equation does it say, well, you start with atmospheric pressure and then you add in some extra stuff. So just be careful of that. Given a question about the pressure depth relationship or something like that, read the question. Does the question say I want the total pressure? If that's true, then you do the pressure depth relationship, that's gauge pressure, and then you add atmospheric pressure to it, which is just a number, it's a constant. And that constant, you don't have to memorize it, that would be on the test. However, if I don't say I want the total pressure or the absolute pressure, then all I want you to do is just give me the gauge pressure. Who cares about atmospheric pressure? So that's its own little subtopic there. How much pressure will an object feel due to the fact that it has gone underwater or inside of a fluid of some sort? Then we had Archimedes Principle. Now, Archimedes Principle is actually a set of relationships. It's not just one equation, but rather it's a series of different little bitty relationships that all kind of interconnect to allow you to try to solve some stuff. And so what do we have? The first thing we have is the phenomenon that when you place an object in a fluid, the fluid obviously has to move out of the way to give the object room. So you put an ice cube in a cup of water. Well, there was water there, but now the ice is there. So the water had to move to allow the ice to sit there. And so usually what happens is the water level rises in the cup. That's called displacement. You have displaced the water. And so one thing that's realized is that the amount the water is displaced, which we call the volume displaced, must obviously be the size of the object itself. Because the only reason the water or the liquid was moved out of the way was to make room for the object. So how much is it moved? Well, how much is the object? So the volume of the water displaced is equal to the volume of the object that you placed into it. Okay, that's the first relationship. You place an object in a fluid, the fluid level rises. How much will it rise? Well, the volume that it rises is equal to the volume of the object you placed in there. The bigger the object, the more it's going to move out the way. Then another relationship we may want is about the buoyant force. When an object is placed into a fluid, it's going to feel a buoyant force. Now, sometimes the buoyant force is large enough to make an object float. Sometimes it's not large enough, and so the object sinks. But no matter what, there's always some buoyant force. And so the buoyant force is equal to, it turns out, the weight of the water displaced by the object. So what happened in an experiment? Someone filled the container to the very tip top with water. They placed an object in the water. So as the water level rose, it overflowed over the cup and they gathered all the water in some second container. All the water that overflowed, they gathered up. Then they measured the weight of that water that was overflowed. And they have a number. It's 2 pounds of water or whatever it is. Then they went to the object and they said, okay, what's the buoyant force on this object? Well, they don't know, but they can experimentally calculate it. And the way they do it is they say, well, how heavy is the object initially? It's a certain weight, 20 pounds. Then when we place it in the water, how heavy does it feel now? Well, now it feels 18 pounds. So it feels lighter. That's what we would expect. You put an object in the water, it should feel lighter. So now it's only 18 pounds. So the difference, which is how heavy it actually is minus how heavy it feels while it's in the water, is 2 pounds. And that happens to be exactly the same as the weight of the water that was overflown from the container initially. And that's what this means. The buoyant force, which would act on an object that you place into a fluid, is the same number as the amount of water that was displaced by that object. If you weigh it, it's that same number. Now, to actually use this in trying to solve a problem, usually this isn't all that helpful. The concept is helpful, but this equation is not, because we usually don't know the weight of the water displaced. What we want are the characteristics, the things we can measure easily. And so what people do is they say, look, I know that weight is mg, right? Weight is mass times gravity. I also know that density is mass over volume. Okay, so I don't know what this mass is. So let me use this second equation to calculate mass is equal to something else I do know. So mass is equal to density times volume. And then I just replace mass in that equation with what I just figured out from density, and I get that the weight is mass, which is density times volume, times g. And I say this is important because I know the density of the fluid. Let's say this is water. Density of water is 1,000. Nice. Volume, V. Well, I already have a relationship for the volume of the water. All I need to know is the volume of the object. So if I want the weight of the water displaced, instead of that, all I have to do is say the buoyant force is density of the fluid times the volume of the fluid times G. Because the weight of the displaced water from this relationship I did over here in red is given by this new equation. And that's more helpful when we do actual calculations. It's the same equation, it's just they rewrote weight as this other thing. And then they went further, one extra step, and they said, hey, don't forget about this little relationship up here, that the volume of the fluid is the same as the volume of the object. And so the buoyant force acting on an object is the density of the fluid times the volume of the object times gravity. And all of this is what we call Archimedes Principle. Those four relationships in green kind of come together. They're all interrelated. They use each other here and there. And this is what we can use to help us calculate stuff with Archimedes Principle. Then there were some extra little things we know that go along with it. First of all, there's something called, which I used just now in Archimedes, I believe, I talked about it. And that is apparent weight. So the apparent weight of an object and apparent weight just means when you place an object in a fluid and you go measure how heavy it feels, it won't be its true weight. It's going to feel lighter. And it'll always feel lighter because there's a buoyant force acting on it. That buoyant force is the force trying to lift up against gravity. So gravity's pulling it down, that's the weight. But if there's another force pushing up, called the buoyant force, then obviously if you measure the weight of that object with this extra force on it, it's going to feel lighter. And so the apparent weight apparent, is the true weight minus the buoyant force. And so with this, we could solve questions like, there's a treasure chest under the water, and you need to build a fancy claw machine that will allow you to pick that treasure chest up out of the water. Now, to design it, you need to know, of course, how heavy or how much force this claw machine has to give to pull up on the sunken treasure. So how do you know how heavy it's going to feel while it's under the water? Well, if you know something about the treasure, you say, oh, there's 10 gold bars in it. Well, I know the weight of each gold bar, so I multiply that by 10. I now know the actual weight of this treasure is blah, 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 1,000 pounds. However, I also know since it's underwater, it won't feel like 1,000 pounds, it'll feel lighter. How much lighter? Well, if you can calculate the buoyant force, which would act on it, then you can subtract that from the true weight, and that will tell you how heavy it would actually feel while it's underwater. How would you get this buoyant force? That's what Archimedes Principle does for you. Use Archimedes Principle, calculate the buoyant force, calculate the true weight separately, put those together, that would tell you the apparent weight of the object. And then the other relationship we have is kind of a shortcut for something like, here's some complicated object, a weird shape made of all sorts of materials. I put it on water and it floats. If I know how much of the object floats, whereas how much of it is under the surface, I can figure out what the density of that object must be. And what this says is the percent submerged equation. And so the percent submerged, or how much, what fraction of the object is under the water, is given by the density of the object divided by the density of the fluid. And so with this type of problem, I can say you have a ship. The ship is on the water, and you notice that 3/4 of the ship is above the surface of the water. Tell me what the density of the object is. Well, I could use this equation and say the percent submerged, if 3/4 of the object is above the water, then 1/4 is below the water. So the percent submerged is 1/4, or 0.25 if you want to use a decimal. So the percent submerged, 1/4 is equal to the density of the object, which is what I want to calculate, divided by the density of the fluid. Is the ship, is the boat on water, then density of the fluid is 1,000. Is it in oil? Is it in honey? What fluid are we talking about here? So that's a nice, easy shortcut equation to get the density of an object, which may be very complicated. Because if we don't use this equation, how else would you calculate the density? Well, you need the mass of the object and you need the volume of the object. Remember, dense is mass over volume. Well, maybe it's okay to calculate the mass of the object. You actually weigh the ship or something. But the volume, calculating the volume could be a very difficult thing to do. If it's some weird shape and there's a lot of air spaces and stuff inside, this is something difficult. However, this shortcut equation means we don't have to worry about any of that stuff. Just look, how much of the ship is underwater, how much is above the water, and that can tell you how to calculate this. And so I believe those are all the topics. Okay, so kind of like 4 little subtopic things here. Bernoulli and continuity go together, and that's problems like you have a water, a pipe system, the pipe changes size, goes up to the 2nd floor. What's the difference in pressures? The pressure depth relationship, a diver goes underwater a certain depth. What's the absolute pressure felt by the diver? Archimedes, this is all about the buoyant force. And usually I kind of put apparent weight with Archimedes too. And then percent submerged. You have a boat, quarter of the boat is under the water. What's the density of the boat? Okay, so that's kind of the types of problems you would expect to see. Little subtopics, each one has its own little set of equations. But each one is not so bad. And each one is fairly clear which equation you'd use for that problem. Okay, especially if you've done practice problems, if you've done a few examples, then you know by how the problem sounds, is this a Bernoulli problem or is this Archimedes problem? So that's it. Those are the topics. Those are the equations, all the equations you would have to know. I believe I don't think I'm missing anything. Little things you may want to know, which will be on the test, but just for information. The density of water is 1,000 kilograms per cubic meter. And I think atmospheric pressure is something like 1.01 times 10 to the 5th pascals. The volume of a sphere, 4/3 pi r cubed. So these are little constant things you would have to know. I would likely be giving these on the test because I make it my own policy, not to just make everybody memorize a bunch of weird stuff. It's all about, can you use this stuff? Question, yes.
So you said that the Bernoulli would be, an example of Bernoulli problem would be the water going through a pipe. You said the pressure and depth would be a diver. And what did you say the examples for the Archimedes and the apparent weights were?
Yeah, so if you remember, I think we did this last time, an example like this last time, but it may be something like you have an object, let's say an object has a mass of 100 kilograms. Let's say it's a solid metal sphere. You have a solid metal sphere of 100 kilograms and its radius is 50 centimeters. And you place it in the water and you want to know what would its apparent weight be. A question kind of like that. And so what you would do is you'd want to do the apparent weight equation, which means you need to calculate the true weight. Well, that's mg, you know, the mass of the sphere. So mass times gravity gives you the true weight. And then you need the buoyant force. How do I get the buoyant force? Well, I use Archimedes principle. Buoyant force is rho times v times g. The density of the fluid, we're in water, that's 1,000. The volume of the object, well, I don't know the volume, but I could calculate it using 4/3 pi r cubed. I know the radius of the object. So I multiply all that out, I get the buoyant force. So now I have the true weight, I have the buoyant force, I subtract them, that gives me the apparent weight. So that's kind of how Archimedes style problems go. They're usually things where you have to calculate the buoyant force or the volume of the object or the volume of the water displaced. Those things are where Archimedes comes in. Especially things that deal with buoyant force, that's Archimedes' principle. And so that's what I would say. That's one way of, if I'm asking about apparent weight needs buoyant force leads you directly to Archimedes. So that's how you'll know. Are there any other questions? All right, well, that's really all I have for this exam review. As I said, Monday, it'll be posted in the morning. Of course, since we're doing the test, there's no class on Monday. It'll be posted in the morning. I'll send an email when it's posted just to let you know. Download it, work all the stuff out, either on that test paper, or you could do it on a separate sheet of paper, depending on how you want to do it. Submit it all back to Canvas. And then by 11:59 p.m. and all is good. If you have any questions, feel free to email me about them, especially the kinds of questions I can ask, and I have no problem answering, I should say, are questions where, you know, I don't really understand what you're asking, or, hey, this number, is this a 20 or is this a 70? You know, things where you're not sure about the question. Things I won't answer are, hey, can you look at number 3 and tell me if I did anything wrong? Or I'm stuck, I don't know how to proceed. Can you let me know what I should do next? I can't do that. This is a test. The point of it is to see if you can do it yourself. But if you're unsure of what the question's asking, if you're confused by the question, or if it looks, you know, my handwriting is bad or something like that, well, obviously I'm going to help with that kind of stuff. So don't be afraid to ask me questions. Just send me an email and I'll answer as fast as I can. Also, as was true before, you're free to use any resources you want, all your notes, any of the videos that are posted. Obviously, you can go online and look stuff up. I'm not going to be there over your shoulder making sure you're not looking stuff up. But I do ask that you work this yourself. Even if you're unsure, even if you don't know if you'll do well, I'd much prefer you doing this yourself without asking someone else than for you to cheat and just write, you know, give someone else's work. I especially hate it when there's cheating going on and the person you cheat off of doesn't know what they're doing either. So everybody gets the question wrong. That's the worst. So just, you know, on the honor system, work these problems yourself, but feel free to go through the notes, look at the practice problems, the solutions, post it on cam. All of that stuff is at your disposal. So you should have no reason not to be able to sit down and work through the problems yourself. But anyway, other than that, oh, also tonight, 11:59 p.m., the homework is due, homework on Archimedes. So don't forget about that as well. If you haven't already submitted it, that homework is due tonight. So definitely do it before midnight. So, and I'll try to grade it as soon as possible so that you'll have it there for you to check out. But other than that, you're free to go and enjoy your weekend. If you do have any questions, of course, stick around and feel free to ask, but I'll see you next time.
Have a good day.
All right, you too. Thank you.
Have a good
Hi, Dr. Rossman. I emailed you about opening up the Bernoulli's homework.
Oh, okay. Yeah. Let me see really quick. Yeah, okay. I did get it. I don't know why I didn't see it earlier. I just looked, just searched for you, and yeah, I have it. Okay, I'll email you back and extend it for you. That's fine.
Yes, sir. Thank you. Take
All right.
care.
Thank you.
I have a question about the homework.
Yes, ma'am.
The first question. So I found the volume first using the radius and then tried to find the density, but I use like P equals W over volume times gravity. Was that the wrong equation to use?
Okay, let's see. So let me look. So the first homework, the first question: metal sphere whose diameter is blah 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 weighs this much. How much would the sphere weigh if placed in water? And you're saying you what thing is it you're trying to calculate right now?
So after I found the volume, I tried to
Okay.
use that to find density. I
Uh-huh.
just think I used the wrong equation. So I'm trying to see which equation I should have used.
Yeah, density is mass over volume.
Oh, okay. So mass would be what, 2,000?
So yeah, let's look. I tell you in the question that the thing weighs 2,000. Well, that's weight. And I know weight is m times g. So if I know the weight is 2,000, is m times 9.8. So that means m, the mass, is going to be 2,000 over 9.8.
Okay.
That's how you can get the mass, and then you could use that to get your density.
Okay. Thank you.
Yeah, so that's definitely something to look out for. Weight versus mass. You could get the weight from the mass or vice versa, but they're not the same thing. The mass is what's important for density. So if I give you the weight, convert it to mass first, and then you use the mass.
Okay. Thank you.
All right, no problem.
Bye.
Bye-bye. Any other questions?
I had one. It was similar to hers, but I just wanted to know, with the water dispersion equation, the vacuum equation, I was supposed to use with the that question.
Let's see. I'm sorry. Can you ask that again? It was kind of muffled a little bit for me.
I'm sorry. With the first question on the homework,
Yeah.
I was I guess confused on which equation. Because at first I thought it was the water dispersion equation, but now I'm not sure.
Yeah, so let's look. The first question, what you want to know is the apparent weight. So when it says how much would the sphere weigh if placed in water, that means give me the apparent weight. And that is the true weight minus buoyant force. So we need these two things. The true weight, well, that's nice. That's given in the problem. That's 2,000. So that's easy. Now we need the buoyant force. Well, the buoyant force from Archimedes is this one right here. And it says density of the fluid, volume of the object, gravity. So if I want density of the fluid, well, that's given in the problem. That says it's 1,000. Then the volume of the object, well, I need that. I don't know it yet. So how do I get volume of the object? Well, I say density of the object is mass over volume. So volume, or there's a better way of doing it. I don't need to do it this way, actually. I'm sorry. I could just use the volume equation. The volume.
I'm sorry. So with that would be with where you're trying to find the volume of the object, and it'll be like 4 divided by 3 times pi r cubed.
That's exactly right. 4/3 pi r cubed is the volume of the sphere. Now the problem doesn't give us r, it gives us the diameter. So I'm told diameter is 60 centimeters, so that's 0.6, which means the radius is 0.3. And so this r would be 0.3 rather than 0.6. That's a little trick to make sure you know people aren't rushing through the question. They know what they're looking at. But that would give us a volume, exactly right. And then of course, G is just 9.8. And so you'd plug all of that stuff into your calculator and you'd have some buoyant force, some number. Now you have the true weight, now you have the buoyant force, you subtract them, and that would give you your answer.
Okay, so, the answer I have gave me a negative number. Was that right? I
Okay,
had a negative 6.867, I mean, negative 6,857.00.
that's possible. Let me see, because I made this question up, I'm not getting from a textbook, and my numbers may be weird. So let me calculate really quick and just see what I get. 0.3 cubed times 4 pi divided by 3 times 9.8 times 1,000. Let me do this again just in case. 0.3 cubed times pi times 4 divided by 3 times 1,000 times 9.8. All right, I get the buoyant force is 1108.35 when I plug that in my calculator. And so if that's true, then it's 2,000 minus 1108. You should get a positive number from that. So if you're getting something else, make sure when you're plugging it in your calculator, do it one piece at a time. Don't try to put everything in on one line, because especially with fractions like 4/3, sometimes it doesn't know, is the pi going to be on the bottom or is it on the top, and all of that. So when you're calculating this piece here, just multiply one little piece at a time. And I just did it twice and I got 1108 from it. So just make sure the calculation's coming out okay.
Okay, I will do that. Thank you.
All righty then.
Have a nice day.
Thanks. You too.